is parking centroid, which are points. These are the centroids of parking lots at UV. Okay. Then the second one I got is Erie County network. And if I right-click this layer and click zoom to layer, I will see that this layer actually contains the whole network of the Erie County. Okay. Now, here is a possibility you encounter. Sometimes when you open a shapefile, you will see nothing. And you right-click and click zoom to layer. It does exist, but this one is not overlapping with that one. And you will be very confused of what happened. Now, before we deal with that, let's talk about another topic called projection. Here is the data we acquired. We acquired a network, including satellite images, roads, and parking lot centroids. And we acquired parking lot occupancies by time of day. This is a table. And we obtained traffic counts and class schedules. Actually, I wrote a program to read the class schedule online from the UV system. Here is the satellite image. And these are the roads of the Erie County, and we want to only focus on this small area, which is UV North Campus. And these are parking lots and centroids. How do we count traffic? We use two types of counters. The first type of counter is a radar counter, which is the one that Andrew is always trying to open in the paper box. And by using this radar counter, we can remotely measure the traffic volume through the 24 hours. So typically we went there to install the counter on a pole in the morning, and we went there to get it back at evening. And sometimes our coordination with the police department was not very good, so they were waiting there trying to see if we are terrorists. So before counting data, we should send a fax to them. Sometimes, because of whatever reason, they didn't receive it. So, and this thing really looks like a bomb, right? So when you see this in the future, don't panic. Another counter we use is the tube counter. So we put a tube across the road. I think you may see it sometimes in Buffalo, right? This tube counter. Okay, now it's geography coordinate system. For coordinate system, we have two kinds of systems. One called geographic coordinate system, the other one called projected coordinate system. In terms of geographic coordinate system, it can be simply summarized by what kind of ball the Earth is. But before that, let's talk about two basic concepts: latitude and longitude. So this is North Pole, this is South Pole, and this is the equator, and we have many parallels. Okay? And if we draw a big circle that passes both the North Pole and South Pole, we get meridians. And there is a meridian called the prime meridian. And it divides the Earth to two hemispheres, Western Hemisphere and Eastern Hemisphere. And when we talk about the coordinates of a certain place, we first use the prime meridian and we measure this angle. And this angle will become the longitude. And then we measure this angle, this will be the latitude. So this point has a coordinate of 80 degrees east, and 50 degrees N. The first one is longitude, the second one is latitude. Now, why do you have many coordinate systems? That's because, accurately speaking, the Earth is not a perfect ball. It can be viewed as an ellipsoid, which has three axes, and the three axes are different in terms of their length. And if we think these two axes are maybe two axes are of the same length, then it becomes a spheroid. But none of these is a perfect ball. And that decides, and if we decide this axis length, then we'll be able to decide the coordinate, I mean the longitude and latitude of a certain place. Now let's look at the surface of the Earth. Many years ago, when we talk about the surface of the Earth, we use the main sea level. It's called geoid. And how do we determine the sea level? It's very easy, right? But this surface is essentially defined by gravity. Look at this line. So this is sea level. This red line is sea level, okay? And this black dashed line is the mathematical model I just mentioned, like a spheroid. These two lines are different. And let's talk about a certain point here. We have a plumb line here. How do we get a plumb line? So if we measure the direction of gravity, when this stabilizes, the direction will be the plumb line, okay, this direction. But when we use a mathematical model, we have another plumb line, and these two are different. So in terms of a position of this place, let's talk about this place. This place on the hill. If we use the spheroid model, you will have an elevation, and you will have a longitude and latitude that's the same to this point, base point. But if we use the geoid, or the main sea level, it must be projected to another place. So it has different longitude and latitude, and you will have different elevation. Do you understand this? Using different description of the Earth or of the ball, you get different coordinates. 3D coordinates. Okay? Do you have any question about this slide? You're so smart. No. After we get the longitude and latitude and elevation, we can already perfectly locate any point on the Earth. But why do we need projected coordinate systems? That's because we want to put a 3D ball onto a flat 2D map. And if it's a ball, how can you put it on a 2D map? We have three ways of doing this: cylindrical, conic, or azimuthal. Let me give you a very simple demonstration or illustration. So in the first case, we have cylindrical. Let's talk about a cross-section. This is the Earth. And if this is cross-section, then any place on the map will be equal, will point to any place here. Okay, you project vertically by perpendicular lines. Okay, this is projection. So you see how it's projected? But there are three kinds of projection systems, and I think you can easily comprehend that none of them has no distortion. But if you take a look at a cylindrical projection, you will find that there is a circle that the outside cylinder gets completely touched with the inside ball. So there will be a line here which touched perfectly. Okay? So that's why they invented another projection system called the universal transverse locator, which is also called UTM. And they use horizontal cylinders to cover the Earth, and they cover it 60 times. I really like this metaphor. So actually, I think the inventor of UTM must be a fan of orange. So you see, this piece is very flat compared to the whole orange, right? And if you divide it into 60 pieces, then you can easily project them on paper without much distortion. Do you understand this? And when we use UTM system, we take a look at US mainland. Now we have a major question. Which zone, which UTM zone are we in?
17.
We are here, right? We are here. This is Buffalo. This is New York City, and this is Albany. But most of the time, we get a map that are located in UTM 18 because they are made by somebody like in not in our area. So very often we see maps with UTM 18. And for each UTM zone is divided into, for each number, for example, UTM 18 is divided to two parts, UTM 18 north, which is to the north of the equator, or UTM 18 south, which is to the south of the equator. And within each UTM zone, we have two numbers or two coordinates called easting and northing. Easting is equal to x, and northing is equal to y. And we use meter as the unit. Within each UTM zone, this vertical center line has no distortion. So we use this as the y-axis. And then we use equator as the x-axis. This is easting. This is northing. And if we define this as the original point, then this axis, this point's coordinate will be 0, 0. And this will be negative, this will be positive. In order to make all the x coordinates positive, we set this as 500,000 meters. Okay, we add 500,000 meters to this x-axis. And if we talk about the south part of the equator, we also add 10,000 kilometers to make it positive. Okay? Now, the reason that we didn't see these and that overlapping is because in this layer we accidentally lost the projection information. So, for a certain shapefile, which is the file, the format you're getting, there is a main file called SHP with the extension SHP. But you also have some other accessory or auxiliary files. And there's one called PRJ for defining the projection. If you lose this file, your files, then you don't have any projection file information in your shapefile. In that case, you may want to repair this. So we have this layer, and it has no projection defined. Then we use this tool. I will explain that later. So we use this tool to click somewhere in this layer. And we see the location. Here's minus 78 something and 43 something meters. It should not be meters. Okay. I think I appended some information to it. No. What does it have? So let me demonstrate it in another way. Okay, let's talk about the Erie network file, shapefile I just opened, and I delete this projection file. Now when I open it, oh, it's still perfectly matched. Let's resume to this.